Hey, this is Mrs. Cribb. We are going to go over a complex thermodynamic problem, and hopefully this will help you. For what we're going to do is we're going to turn 7.5 grams of ice, and we're going to melt it, and then we're going to turn it into steam at 120 degrees Celsius. And we're going to need to figure out the total amount of energy it takes to do this. We're going to start down here where this blue dot is. We will have solid ice at negative 10 degrees Celsius, and in this area right here it is still ice. It's still a solid. We're going to use this amount of heat to heat up that solid ice until it reaches this point where it is a liquid at 0 degrees Celsius. Right here the line's pointing to the temperature. And then we're going to use the next set of energy, the next amount of heat, because we're adding heat into this system. We're going to add more heat, and it's going to be latent heat because it's lazy and it doesn't change the temperature, just the phase changes until we get it to 0 degrees liquid. And then we're going to add the third amount of heat to raise the temperature of the liquid to 100 degrees Celsius. The fourth amount of heat will be added to change it from 100 degrees Celsius liquid to 100 degrees Celsius steam. And the fifth amount of heat will be added to turn it from 100 degrees steam to 120 degrees steam. So the latent heat areas are these right here, lazy latent heat, and that's where you don't see any change in the temperature. Notice the temperature is the same on both sides. Up here, another lazy latent heat area. The temperature is the same and never changes until it all the way converts from liquid to gas. All the way converts right here from a solid to a liquid. The sensible heat areas are the ones where you could feel it changing. You use a thermometer to check that temperature change. Okay, let's start off with calculating Q1. Q1 is in the sensible heat area, and we use these formulas. All sensible heat areas use this formula. MC delta T. M is the mass, 7.5 grams in, so M is mass for this particular equation. C is the specific heat, so M is mass, C is specific heat. And you have to look that up on a chart. So I'm going to write these things up here. M is mass, C is the specific heat. And you find the specific heat on the chart. Let me go look at a chart that I've created for you. Here it is, the specific heat. Now, I have the specific heats of water, of ice, and of steam right up here. They're also contained down here. There's water and there's ice. So we're dealing with ice at this point. So we're going to use 2.05. We'll use this one that's up here, joules per gram degrees Celsius. 2.05 joules per gram degrees Celsius. So I'm going to write that down. 2.05 joules per gram degrees Celsius. And then delta T is the change. And remember that delta T is equal to the final temperature minus the initial temperature. Final temperature minus the initial temperature. So the final temperature is right here for the first section. See, the initial temperature is negative 10 degrees, and the final temperature, when we get over to this section, right there is a 0 degrees. And there's the temperature, 0 degrees. So 0 minus a negative 10 would give us 10 degrees Celsius. So it's a positive number, and that makes sense because it's heating up. And now, notice that the units cancel. Grams, grams, degrees Celsius, degrees Celsius. The only unit left is joules, and now we're going to put that into our calculator and just calculate that value. Alright, here's the calculator. Okay, so let's put this in there. 7.5 times, oh, I forgot to turn on. Here we go, there. 7.5 times 2.05 times 10. And I get 153.75. I'm going to use two significant figures, two decimal places, or I mean so two significant figures throughout this. So 150, that would turn into 150. 150. Right, write that down. 150 joules. Okay, that's Q1. All right, now, so we just completed Q1. We've added this amount of heat from here to here. This is where we are heat-wise. And now we got to go Q2 and go get the next amount of heat. So for Q2, the formula is the number of moles total times the heat of fusion. Delta H of fusion. And I don't know, again, why they use fusion for the melting process. All right, we don't know the number of moles, so we have to calculate the number of moles. So I need the molar mass. I'm going to do it up here real quick. For water, H2O, we have 2 times 1.01, and oxygen is 16. Add that together. 18.02 grams per mole is the molar mass of water. All right, now, so I have 7.5 grams of water. I'm going to turn it to moles. So I'll do that over here real quick. 7.5 grams. 1 mole is 18.02 grams. Grams cancel. And I just have to calculate the number of moles. Turn my calculator back on. And 7.5 divided by 18.02. It's 0.42 significant figures, 0.42. I'm using 2 significant figures here. 0.42, 0.42 moles. So we can put that into this calculation. 0.42 moles times the delta H of fusion. And so I need to look up the delta H of fusion. So I'm going to look at the chart over here. The delta H of fusion, here they are. Water. The delta H of fusion, there's the one with fusion. This one right here, fusion, is 6.01. 6.01 kilojoules per mole. 6.01 kilojoules per mole. All right, so let's put that in there. 6.01 kilojoules per mole. And we just have to multiply that out to get that value. And that's 0.42 times 6.01. It's 2.5. 2.5. 2.5. Okay. 2.5 kilojoules. The moles will cancel out right here. Moles and moles. So that's Q2. Now, so that gets us from this area. We added that many more joules to get to this point. So now we got to calculate Q3. Q3 is in another sensible area. So MC delta T. The mass is 7.5 grams. The specific heat, now we have the specific heat of water, because it's this right here is where it's liquid water. So we're heating up the water. Before we had ice, and now we need the specific heat of liquid water. So I go back and look at my chart. And for water, the specific heat is 4.184. Right here. And down here it just says 4.18. So we're using these up here for the moment. 4.184 joules per gram degrees Celsius. So we're going to add that in here. 4.184 joules per gram degrees Celsius. And that's the C, and the delta T. What's the delta T for the third part? Well, the final temperature is up here, and the initial temperature is down here in this part. So T final is 100 degrees right here. So 100, and the initial temperature is 0. So 100 minus 0 is 100 degrees Celsius. All right, now cancel out the grams, cancel out degrees Celsius. We have joules. And so let's pull our calculator back up again, and let's figure out what it is now. Turn it back on. And 7.5 times 4.184 times 100 is 3138. 7.5 times 4.184 times 100 is 3,138, and 2 sig figs is 3,100. So 3,100. 3,100. The unit that didn't cancel is joules. Okay, now we need to calculate. So that's getting us from Q3 to Q4. So we're right here now. We just added all this much more heat. Now we got to add the next amount of heat. So Q4 is in a latent lazy area again. We use the moles times this times the heat of vaporization, the delta H of VAP, basically. So moles times the delta H of vaporization this time. The number of moles is the same, 0.42 moles. And then we have to look up the delta H of vaporization. Here, let's see if we can find it. The delta H of vaporization, over here, somewhere. There it is. Water and delta H of VAP, 40.7 kilojoules per mole. 40.7 kilojoules per mole. So we go back over here and write that in. 40.7 kilojoules per mole. All right, moles cancel. And we just got to multiply that out using our calculator again. 0.42 times 40.7 is 17. Two significant figures, 17. Okay, 17 kilojoules. That's Q4. So now we've gone from here, added 17 kilojoules to get to Q5. And now we have to go just a little bit farther. And this again is a sensible heat area, so we'll use Q equals MC delta T. So Q5 equals MC delta T. The mass is 7.5 grams. The specific heat, now that we have the specific heat, everything over in this area is steam. Okay, this is all steam. So I need the specific heat of steam. How much heat does it take to warm up steam? So I'll go look in my chart again. For steam, it's 2.01 joules per gram per degree Celsius. Right here, 2.01 joules per gram degree Celsius. So 2.01 joules per gram and per degree Celsius. The grams are going to cancel. And I've got to do the delta T still. Okay. The change in the temperature this time. All right. The final temperature is right there. That's 120 degrees Celsius. The initial temperature is right there. That's 100 degrees Celsius. So final minus initial. It's going to be 120 minus 100. So that's going to give me 20 degrees Celsius. Again, it's a positive number because we're still heating things up. The C's cancel, and now we have to calculate this one. Turn back on the calculator. 7.5 times 2.01 times 20 is 301. But we're going to do 2 decimal places, or 2 sig figs, it's just 300. So 7.5 times 2.01 times 20 is 300. 300 joules. Okay, now I want you to notice, here we have Q1, Q2, Q3, Q4, and Q5. All those, because we have just now finished, we've gone all the way to the very end, added the last amount of heat. So what would be the total amount of heat then to do this conversion? All right, the total heat is going to be Q1 plus Q2 plus Q3 plus Q4 plus Q5, or 150 joules plus 2.5 kilojoules plus 3,100 joules plus 17 kilojoules plus 300 joules. Okay, Now, the only problem is I have kilojoules and joules at the same spot, so I'm going to need to convert. So I'm going to go ahead and convert kilojoules to joules because it's just multiplying this by 1,000. So this is, instead of 2.5, it's 2,500 joules. Because I'd move the decimal places 3 spots. 1, 2, 3. Okay, same thing over here. 17 times 1,000 is 17,000 joules. Now add all those together to get the final total amount of heat it takes to change 7.5 grams of ice at -10 degrees to steam at 120 degrees. Okay, so now 150 plus 2,500 plus 3,100 plus 17,000 plus 300. 23,050. 23,050. And if you use significant figures, the 17,000 ends in the thousandths place. So my number has to end in the thousandths place. So it's 23,000 joules. That's the total amount of energy it took to turn -10 degree ice, 7.5 grams of it, to 120 degrees of steam. I hope that helps.